The objective of this video is to derive the equivalent single-phase circuit of an induction machine in terms of machine design variables. I'm assuming that at this point of your coursework, you've all seen the equivalent single-phase circuit of an induction motor, and it's what I've drawn over here. The idea is that across these terminals is the phase U voltage, or it could be the phase W or the phase V voltage. It's one of the stator voltage terminals. And going in here, we've got stator winding resistance, leakage inductance. We've got a magnetizing inductance. And then going on this path over here, we've got our equivalent phase of a rotor circuit. This circuit captures most of the salient information about an induction motor, and it's studied a lot from a drives perspective or an operation perspective. It's helpful to be able to relate this circuit to machine design variables. So our purpose in this video is to take the fields theory that we've been developing in this class and the operating theory of the induction motor that we've been developing and use it to derive this circuit. Before we get going, let's recall some of the results that we have derived so far for induction motors. First, we start every video by making a claim about the total air gap field as being equal to the magnetizing field. That is B delta times the cosine of P alpha minus omega t. And here I've provided our sketch that we've been using for field quantities, and so we're labeling B delta up here. This is drawn for a two-pole equivalent machine. So from this air gap field, if this is the total air gap field, we've shown that we can write an expression for the voltage in an individual rotor bar, where I is the rotor bar number, so 1, 2, 3, 4, so on, as being this expression here, which goes by the cosine of a slip times our stator frequency, and then has a phase angle related to the electric angle of the specific slot that we are discussing. We can write this as a phasor quantity, and we can use this to derive the phasor of the rotor bar current, where we've already described our rotor impedance as being this quantity, and that is often referred to in our notes as having a magnitude and an angle of zeta r, which depends on slip because the impedance depends on slip. From this, we can derive our rotor bar current for any rotor bar, and we've got an expression written out here, which we'll be using in today's video. And from our rotor bar current, we know what the current of all other rotor bars are, and so we can derive the total current linkage that the rotor creates, which acts on the air gap, as this expression. Or we can write it in terms of our magnetic field over here. So by assuming this quantity and a certain value of slip, all of these quantities drop out. All of these physical parameters of our rotor circuit drop out. Now, to derive the equivalent circuit, the first thing we're going to do is we're going to figure out how to relate the rotor current to the stator current. You've probably heard in your coursework about inductances or currents of the rotor referred to the stator. We're going to go ahead and figure out what that means. And our first stop in doing that is acknowledging that, again, B delta is the total field in our air gap. And so as such, it must consist of a portion that has been created by the rotor and a portion that has been created by the stator. And so, of course, we know that fields in an induction motor are always created by current. So we can see that the portion that's been created by the rotor has been created by our rotor current linkage, multiplied by mu naught and divided by our effective air gap length, the standard way that we convert any current linkage into a magnetic air gap field. And we can do the same thing for the portion that's created by the stator winding. It must simply be mu naught times our total current linkage from our stator winding divided by our effective air gap length. And if B delta is actually our total air gap field, that means that our stator must be carrying current to create two fields. One component of current must be creating that total field, and a second component must be carrying current to create a reaction to the rotor field to cancel the rotor field out, right? So if the rotor, we know that the rotor is creating a current linkage, and so therefore it is creating a field. And our stator is responsible for making sure that we have exactly B delta field in the air gap. Therefore, it must also be creating a field that is canceling that rotor field out. And so this allows us to now make a leap and talk about current linkage. If we know that this is what our fields must be doing, then we can talk about what our current linkage looks like. And so similarly, our current linkage from our stator must have these same two components that directly map to the components we talk about above. And now what we're going to do is we're going to create expressions for what our stator phase currents must be. We're going to consider the phase currents to consist of the sum of two components. One component that creates this field, and a second component that creates this current linkage. So one component creates this current linkage, which is our magnetizing current linkage, and a second that creates our reaction to the rotor field. And so we have two things to figure out. One is what is the magnitude of those currents, and the second is what is the angle of the currents. And we'll recall that in our winding design unit, we came up with an expression that relates the cumulative current linkage of a three-phase winding to the magnitude of current in that winding. A second thing is the angle of the currents, like we were mentioning. And I'm going to splash up on the screen the notes from our AC machine design sizing lecture. And in this lecture, we found that if we have three-phase stator currents, and if they go by the angle alpha W, they end up creating a current linkage on the air gap of our machine that goes as N times alpha minus alpha W, and N was just equal to P. So they create a current linkage. If we know our current linkage expression, in our case we do, we've got an expression for what our current linkage should be for both the magnetizing field and the reaction to the rotor field. So we can take that current linkage expression, and we can take the angle, alpha W, and we can feed that into what our three-phase motor currents should be in order to create that current linkage expression. So we're going to do that now in order to construct expressions for our three-phase currents that are required to create the magnetizing field and the reaction field. So remember, the current linkage is going to be at angle P alpha minus alpha W, and then our currents should have the argument of alpha W. So this quantity right here would be alpha W for the rotor reaction field. And this quantity right here is going to be a negative alpha W for our magnetizing field. And so for our magnetizing field, we get these three quantities. And you'll see that for magnetizing field, or for the theta delta component, I'm referring to our current with a subscript of M. So we've got stator current I, MU, IMV, IMW, and it has a magnitude of IM hat, which we can obtain by solving this expression up here, where the left-hand side is just equal to theta delta, and the right-hand side has an IM hat over here. And we're doing the same thing for our rotor reaction currents. So now we've got we're calling this I hat prime subscript R, and the prime is this referred to stator business, because this is the portion of current that has to flow in the stator winding that is due to behavior of the rotor. It's due to rotor currents. If the rotor currents were 0, this would be 0. And we can figure out what this IR hat should be, again, through this expression up here. So we'll do that now. We're going to take this quantity right here, which is right here. So we're going to take this quantity, and we're going to set it equal to this over here. So remember, our responsibility with a stator is to create a current linkage that's equal and opposite to the current linkage created by the rotor. So the amplitude of this current linkage, as created by the stator, is provided by this, and the amplitude as created by the rotor is provided by this. So we can equate these two terms to solve for IR hat prime. So when we do that, again, this expression right here is taken from this equation. This right-hand side over here is taken from our result from a previous video. When we do that, we can define a ratio that is the rotor current magnitude divided by the rotor current referred to the stator. So that is the rotor current magnitude divided by the amount of current, or the magnitude of the current component that flows in the stator due to rotor current, as being this quantity over here. And this is, you can kind of think of this like a turns ratio in a transformer, where your rotor is your secondary and your stator is your primary. So this relates the rotor current to the stator current that's required that flows in order to support that rotor current. And we're going to make one other point here, observation. And we've considered this special case a couple times where our rotor impedance is equal to 0. And so here we can note that if our rotor impedance is 0, if this quantity here is 0, we can see that our rotor current referred to the stator will lead the magnetizing current in the stator by pi by 2. And we're going to flesh that out a little bit more very soon. And so again, IR hat prime is our rotor current referred to the stator. Our total stator current in phase U is going to be our magnetizing current plus our rotor current referred to the stator. And we can write this in phasor form over here, which we get the following complex quantities. So this is all following directly out of these expressions we've got up here. And now we can draw the phasor diagram for this. We've now accomplished our first goal. Remember, our first goal was to relate the rotor current to the stator current. And that is precisely what we have done. We've got a ratio for how our rotor current maps into a component of current in our stator waveform. Next, our goal is to relate the stator phase U voltage, or EMF, to the stator current. So first we had to figure out how the stator current relates to the rotor current. Now we're figuring out how the stator current relates to the back EMF of the machine, or the phase U voltage. And so we start with the observation that the phase U voltage is due to B delta. And B delta, of course, as we've just established, is due to our magnetizing current component. And so we're going to start this by constructing an expression for our phase U voltage related to B delta of alpha. And we're going to draw from our star of slots and winding factor lectures in order to do this. So if you go back and you look at our winding factor lecture, we defined our winding factor as relating to our phase U terminal voltage. And if you recall, we came up with an expression for the voltage in this imaginary slot 0 phasor in terms of the magnetizing field of our machine. And so this is our star of slots video, and you can see we came up with this expression right here for our voltage phasor in imaginary slot 0 as being ZQ times L times omega by P times R times B delta V. And this is very familiar to us at this point. This is the same expression we have for our rotor slots, except for you have an S multiplied in there. So now we're ready to write an expression for our phase U voltage. We're just going to copy this over, and we're going to note that N for us is equal to the number of coils in series, that's ZC, N is the number of coils in a phase, and as defined in that video, and that's what we've been referring to as ZC later in the course. So we can start plugging quantities in that we just reviewed. We'll plug in our quantity for this imaginary slot 0 phasor. So as we do this, we get this expression right here, and we can note that for us, B delta phasor has an angle of 0. That's because we've declared it to up here at the beginning of our problem statement. So there's no phase offset in here. Next, we're declaring that our winding factor has an angle of j pi by 2. And that is because we are declaring that at time 0, our B delta is going to be oriented along the horizontal axis. That must also mean that our magnetizing current linkage is oriented around along the horizontal axis. And so if we look at our winding factors video, we can see that this is only possible if we consider that we have a coil or a phase winding that is centered along the horizontal axis, which for us would mean that it has a winding factor angle of a positive pi by 2. And so now we're ready to take the leap of relating B delta to IM. And we're going to note that, of course, B delta is related to our current linkage that's required to create it, as this over here on the right, and so we can plug that in. And the peak of our current linkage is again related back to IM hat by this expression up here, where this is an IM hat. So we're going to plug that in. And then we're going to rearrange terms and clean things up. And so you notice here, when we write this expression in this manner, we end up having a term out in front, which is multiplied by omega, and then the IM phasor. And so this becomes the form of a voltage phasor that's caused by an inductance and a current phasor. And so we can identify that this term right here must be the magnetizing inductance of the machine. And this is a milestone result. We've just derived the magnetizing inductance of our equivalent circuit for an induction machine. We'll show you how that fits into the equivalent circuit shortly. So we're saying that our back EMF is going to be rotated from our magnetizing current by pi by 2. And it's going to relate to our magnetizing current through our magnetizing inductance. So we can add this to our phasor diagram above. Our back EMF of phase U is going to point up vertically. And so we can see from this diagram that this angle right here that separates our rotor current referred to the stator is delayed from the phase U magnetizing back EMF by the angle of our rotor impedance. It's an interesting result. We're now ready to sketch our equivalent circuit, or our first pass at an equivalent circuit. But before we do that, I want to comment a little bit more on this magnetizing inductance and I guess a bit of a sanity check on how this all fits together. So from your prior coursework and thinking about flux tubes and reluctances, in previous classes you've come up with an expression for inductance as being the number of turns squared on a core divided by the reluctance of the path. And reluctance is equal to length of the path divided by mu a. And so this is kind of a crude sanity check to make sure that we have our inductance in a form that we expect. And so you can see from the sanity check expression, we certainly have mu. Our air gap has a permeability of mu naught. N squared is like this term over here, right? N squared is the total number of turns on a core. Well, that's what we have here. We've got our number of coils squared times the number of turns per coil squared. So that is N squared. Our length for the field path is our air gap length. And then the rest of this somehow represents the area. We've got winding factor worked in there because not all the flux links is linking all the coils the same amount, etc. But so we can see that this does in fact make sense. We are aligning with the form of an inductance expression that we expect. Great. So we just found the magnetizing inductance of our machine. Let's now go ahead and try to draw our single-phase circuit. And so we're able to say that we've got a voltage, which is our back EMF, that sees an inductance in parallel with a current source. And so we know this to be true because we've already written out an expression for how our phase U stator current sums as the magnetizing current plus our rotor current referred to the stator, and these had these angles associated with them. So the magnetizing current was at angle 0, the rotor current referred to the stator was at an angle of pi by 2 minus zeta r. And so I've written that in here. Stator current is at or magnetizing current is at an angle of 0 degrees, and then rotor current has an angle of pi by 2 minus zeta r. The magnitude of our rotor current is equal to our rotor current divided by that turns ratio that we defined up here. And I see I forgot an S on it. And we know that the voltage, our back EMF voltage, is equal to the voltage drop across our magnetizing impedance. So this matches this equivalent circuit. But this is still a far cry from the full equivalent circuit that we showed up here. So how do we get there? Well, we got to work on this rotor branch a little bit. And to start with, we can talk about the current in individual rotor bar. And we've already derived this, we spent a lot of time on this and how we can relate that to the voltage induced in our rotor bar due to B delta and our rotor impedance. And so we get it in this form here, which this form looks an awful lot like this form, except for that we've got a pi by 2 issue, right? We've got a pi by 2 here and we have a negative P alpha I there. And so what we can do is we can arbitrarily choose to think about a rotor phase or a rotor bar that is at angle P alpha I equals negative pi by 2. And if this bothers you, you could imagine that you've got your rotor already rotated to some arbitrary angle to get you this phase offset. But at any rate, it's general and it's proper to say that you can make this expression right here be a negative pi, be pi by 2, so that you're studying a phase that has this characteristic. And so what our goal here is to write an equivalent circuit for our rotor branch in terms of a dependent voltage source that we can map back to this EMF. And we're set up to do this pretty well. We've already been talking about how our rotor, a single phase of our rotor circuit has this impedance, this leakage reactance, this leakage inductance, and this rotor resistance. The only missing piece is what should be the magnitude, or how can we relate our rotor voltage to our EMF. And so what we're going to do is define yet another turns ratio, where we're saying that, well, we know that our rotor voltage magnitude can be calculated like this, so we can divide that by the magnitude of our EMF and figure out a mapping so that we can express this voltage source as simply being a dependent voltage source times a turns ratio on that. So that's what we've done here. We've got this quantity up here, right? And now we can say, okay, our back EMF, we just derived it up here, was related to B delta like this. So we've got this down here. And if we cancel terms, we end up getting a simpler expression on the right side. Our slip times number of pole pairs divided by 2 times the total number of turns in series of our stator winding times our fundamental winding factor. And you can see that it was critical that we found a rotor phase where our back EMF had this phase angle, because that is the phase angle of our stator voltage. And so what we end up seeing is that these two circuits are related, right? If we take the back EMF from this circuit, we can get the voltage that's acting in this circuit, and that is causing a current to flow. Well, that current feeds into this expression here, which causes a current to flow in this circuit. And so now we can substitute this circuit in for this voltage, or into this dependent current source, and thereby derive our final combined equivalent circuit, the final form of our equivalent circuit. But let's make a few comments here about these two circuits before we do that. Okay, the first comment is that this circuit structure that we've set up here looks like a transformer with a different turns ratio for voltage and current. So normally you've got the same turns ratio for voltage and current in a transformer. That's one of the requirements. But here we can see that our voltage transforms in a different manner than our current transforms. We've got a KUR, which is of this form over here, versus a KRS, which is a different expression. The second thing is that this circuit up here, this steady state circuit, is at a frequency of omega, our stator frequency. Well, this steady state circuit over here is at a frequency of S omega. So when I'm talking about this dependent voltage source, I'm not bringing the frequency with it. I'm only talking about the phasor. I'm only talking about the magnitude and phase angle of it. And so, you know, this matters for the impedance, for the reactive impedance. The inductance is going to have an impedance of J S omega times L R sigma, whereas this inductor is going to have an impedance of J omega times Lm. So let's start to combine the circuits. And I'm just going to start by telling you that it's going to take this shape and eventually get to be the more complicated shape we showed at the beginning of the lecture. And so start from the perspective of knowing that it's going to take that shape and then see how it happens. And so we've already established that our rotor current is going to have this solution to it. This is the magnitude of our voltage phasor. Here is our impedance. And we know that the current in our equivalent circuit branch, so that's this current right here, is going to have this form. Well, we picked a rotor phase so that the back EMF works out to give us that angle. And so we can say that that current is just simply going to be our rotor current from solving this equivalent circuit divided by KRS, where KRS was that turns ratio up here. And so we end up getting this expression here where we've got our rotor current in this branch in terms of our voltage, our back EMF, divided by our phase impedance of this circuit here. And so from this we can see what ZR prime must be, and it must be the combination of these terms. So our equivalent resistance in our phase circuit, or in other words, our rotor impedance referred to our stator, is equal to KRS divided by KUR. And when we work the math on this, we end up with this expression over here. And you'll see that I've pulled the 1 over S out to the side, and I'm defining this portion of the expression right here as this quantity called rho. This is this is a definition that your book makes, and it's helpful to have this quantity with the 1 over s pulled out to the side for reasons that you're about to see. So when we talk about the impedance of our rotor circuit, that was this circuit over here, we're again evaluating it at the frequency of s omega. So we get this expression. That's pretty straightforward. Now, when we bring that over to the stator side by following this relation up here, that is this relation, we end up getting this expression. So we have our leakage inductance term has s omega p, omega times our rho value that we've defined right here, times L r sigma, but then divided by s. And so these two s's cancel out, and you're left with this expression, which is why we wanted to separate the 1 over s from rho, so that wouldn't appear here. So now, at this point, we're ready to say what r prime is and L r sigma prime is. So L r sigma prime is simply rho times L r sigma, and R prime is simply rho times RR. All right, so the next point in deriving our equivalent circuit is that we note that the total active power that crosses the air gap, that leaves the stator and goes to the rotor, is composed of ohmic losses and mechanical output power. So in our equivalent circuit up here, we can see that we're modeling the total power that's going to the rotor branch as the power into this resistor right here, as this current going to this resistor represents a power draw. But in fact, that power has two components. One component is the ohmic losses in the rotor cage, which we can calculate in the standard way as I squared R. And then the second component is our mechanical output power. And for this reason, the convention is to separate this R prime by S term into these two components. So we've got our ohmic loss components, which is just this expression up here. And then we've got our mechanical output power, which is this expression over here. So you can verify that if you add these two components up, you get this expression again. And so now we're finally in a position to draw our final equivalent circuit, which we splashed up on the screen at the beginning of the video. So here is our component for ohmic losses in the rotor. Here is our mechanical output power. We've got our current phasor for the magnetizing current. We've got our current phasor for the rotor current referred to the stator. One thing that didn't show up in our derivation is that there's this resistance right here, which is meant to model core losses in the stator due to, this is eddy current hysteresis losses in the stator. Another component of note is we've got an LS sigma, which is a stator leakage inductance, and an RS, which is our stator resistance. So at this point, we have derived the equivalent circuit of the induction motor. We can make a couple comments here quickly. If you solve this circuit, you can figure out the torque emitted on your shaft, the electromechanical torque, as being your output power divided by your rotational speed. So the power consumed in this resistor here divided by the rotational speed. And if this is a three-phase circuit, so this would just represent 1/3 of the total power. Another thing to note is that when we've been drawing our torque slip curves, and we get characteristics, we've drawn this a couple times where we have a characteristic that looks something like this. That's a horrible drawing. There we go. This characteristic can be found by solving this circuit, this whole circuit, under a condition of constant line voltage, but variable slip. Because remember, on the x-axis here is our value of slip. And so that is how you can derive this torque slip curve. You could have also derived it from our field quantities based on our previous lectures, but this provides you a circuit-based approach to deriving this. So that concludes this video. In summary, in this video, we have derived the equivalent single-phase circuit of an induction motor in terms of our machine design variables. We've used the language and the results of our machine design course to come up with the equivalent circuit of the induction motor. And this is especially useful for this motor because this equivalent circuit is so prevalent when describing the induction motor and is used as a means of understanding so much about the machine. So it's very helpful for us to be able to describe this circuit and relate this circuit parameters to our AC machine design quantities that we use when designing and analyzing machines. And we did this by making an argument about the total air gap field being produced by a rotor component and a stator component, and then relating this via current linkage expressions that we developed in our winding design unit and the induction machine unit to be able to draw a phasor diagram of the machine. And then we've derived the magnetizing inductance of the machine along the way in order to get an expression for our EMF across the terminals of our machine, across our magnetizing terminals. And then we've developed this via something along the lines of a transformer analogy. So we've come up with equivalent circuits that were coupled via dependent sources, and then we took those dependent sources and we were able to come up with a single equivalent circuit in the end.